There we go. All right, so today we are marching towards the second exam, right? We have a couple more sections to finish up chapter 7. These are excellent sections because you kind of get some review in these sections naturally, and we'll see this kind of throughout the problems that I've picked for today and everything. But 7.8 is talking about improper integrals, and kind of throughout all of Calculus 1, whenever we integrated things, there's a whole bunch of stuff in our calculus textbook that says basically, if you want to find the antiderivative or if you want to integrate with continuous functions. So the hypotheses that we've always had, like when you apply the fundamental theorem of calculus and all this sort of stuff, is that we have a nice continuous function. And the question has to be asked, right? Well, if you have a discontinuous function, right, is there still a way to find an antiderivative or do some definite integral and calculate area under a curve and all that? And the answer is sometimes yes, right? And this kind of leads us to this notion of improper integrals. And that's really what this first one is all about here, is that we wanted to integrate over some discontinuity, right? If you plug in 0 here, that doesn't make a whole lot of sense. And yet 0 is on the interval from -1 to 1. And if we just try to apply the fundamental theorem of calculus, notice that it does it wrong. And again, because the hypothesis of the fundamental theorem of calculus is that you have a nice continuous function. Here we don't have a continuous function, so it just doesn't work. You can't apply it. And so we learn that the correct thing to do here is actually split up the integral. We go from -1 to 0, and we pay special attention to that discontinuity bit, and then you go from 0 to 1. All right, and you just carefully evaluate this, and sometimes it works out and you get a nice finite number. That is possible, even with a discontinuity, and sometimes it doesn't work out, right? And in that case, probably it usually goes to like infinity or negative infinity, or you could have one of these weird like oscillation cases or things like this. But yeah, kind of all of these are very much possibilities. And that's kind of how we deal with improper integrals. And this is, I would say, the first and maybe most natural case. However, in our class, thinking about what we're going to be doing in chapter 11, we're going to be talking a lot about series. And series, in particular, we're going to have something called the integral method for determining if a series converges or diverges. And in that case, you actually become very interested in these kind of type 2. And we're not going to use the language, type 1, type 2 so much in this, but, the textbook does kind of bring this up. Oh, sorry, I got these backwards. So the type 1 is where you go off to infinity or negative infinity, and the type 2 is the discontinuities, which is kind of backwards for me because I think the other ones maybe make more intuitive sense. But again, we're going to be using this case, particularly here. We're going to have a lot of things going off to infinity, especially in chapter 11. And so we're going to need to have a good handle on improper integrals. So really, this is kind of, it's a nice section and everything, but it's really a stepping stone into chapter 11. In particular 11.3, when we're going to have the integral test for telling if a series converges or diverges. And again, just kind of when we use this language here, convergent means that the limit exists, that it goes to some real finite number. And if it doesn't, then we say that it's divergent. So quite often, many cases that we'll see, we'll say that it like diverges towards infinity, that it gets very, very large, and that's why it doesn't converge. Or sometimes it diverges towards negative infinity. And again, maybe you could have one of these weird oscillating situations, in which case it doesn't diverge towards negative infinity or infinity, but the limit doesn't exist. And kind of we talk a little bit about that like down here or so. So it'd be a case where it just kind of oscillates back and forth. It doesn't go to negative infinity, it doesn't go to positive infinity, but it doesn't go to a single real finite number. Okay, and then, you saw in the video kind of how we, again, just kind of pay careful attention to either if you're going to infinity for your x values, or if you're integrating over a discontinuity. And that's kind of the big point for this. All right, so that's kind of the videos in a nutshell. Yuan, what's going on in the Q&A? Anything that we should bring up here?
First thing is asking, do you have a different definition for the conversion, diversion?
A different definition other than the one presented here?
I think so. He said he's struggling to understand it conceptually.
Sure. I mean, a simpler version of this that is right maybe 95% of the time is divergent means infinity or negative infinity, and convergent means any other finite real number. So if you get something like 50 or 13 or negative, pi or what have you, that all means that it converges. And if it doesn't go to any single finite number, if it goes to something like infinity or negative infinity, those are going to be the classic examples, then that means that it diverges. And again, that's kind of a little bit simpler, and it's correct about 95% of the time. Good. It looks like we have a student with their hand raised. Why don't we go ahead and call on them? Ian, you got the floor.
Hi. So since there's a wellness break right before the exam, there's no quiz on that Tuesday, right?
That's correct. And there's also no recitation then.
Okay, thank you for clarifying.
Yes. Yep, no problem. That's a good point that should post on Piazza and on the D2L. But I'll try to emphasize that, especially next week when it's very close, because we still do meet on Monday. We'll have class and review and all that sort of stuff. And then Tuesday and Wednesday, you get this wellness break thing. And then Thursday, we're kind of back at it. Classes are resumed and we have an exam that night. So, yes. All right. Good. Well, why don't we go ahead and peek at, oh, sorry, I see Arian has his hand up. We'll call on you and then we'll look at the new stuff for today.
All right, so can you hear me?
Yes, sure can.
All right, why is there an exam right after the wellness break? I feel like if you have an exam during the wellness break, you're going to be studying for exam. It's very counterintuitive.
Yeah, it's got, these wellness breaks are something new because, MSU got rid of the spring break, kind of following the lead of a lot of institutions, just not wanting students to necessarily do a bunch of traveling and then come back with COVID or something like that. That's my best understanding. And it's kind of interesting. So they're wellness breaks. There's one that's like right before the final exam. And then there's one kind of, in the middle of stuff. And so, yeah, it's just kind of how things fell. And again, kind of it's in line with how the other wellness break is right before the final exam. I agree that you're probably going to be doing some studying, but hopefully you also take a bit of a break.
So the math section basically hates all students. Is that correct?
No, not at all.
Come on, you put it before the exam and the other exam. You're just not giving any wellness, it's mostly stressness.
They did not let us choose these things. They were, just told this is what they're going to be. We didn't get to choose that it was right before the final exam, and we didn't get to choose this one either.
All right, thanks, Ryan.
Yeah. All right, well, with that gloomy sadness lingering over the class now, let's do more problems. All right, example number one. Here's one of these that goes off to infinity, right? So we can see that there's an improper integral happening here. And again, kind of formally, whenever this happens, it's a good idea, really, when you're showing your work, thinking about partial credit and all this sort of stuff, when it means that something is going off to infinity, that's not, we have to be careful with the definition here. So the way that we do it in the pre-class videos and kind of how many textbooks and everything do it, in order to be careful about this, we're going to be taking the limit as some other variable goes off and becomes very, very large. So the limit as t goes to infinity of the integral from 2 until t. So this is formally what we mean by this integral from 2 to infinity. Now with this, it is nice and well defined. So we can evaluate out this definite integral, and then we're going to do this limit, right? We're working inside out, kind of like we do in many, math examples. So let's go ahead and evaluate out this definite integral here. So let's see, this is the same thing as x to the negative 7th power. So whenever we integrate using the power rule here, we're going to raise up our power by 1. So this goes from -7 to -6. And then you multiply by the reciprocal of your new exponent. Of course, it's never a bad idea to be a little bit paranoid. Take the derivative of this, see that you get back to where you started. Now we're evaluating this from 2 all the way until t. And remember, this t is something that eventually we're going to let be very, very large, going off to infinity. So we'll say the limit as t goes to infinity. And now we're going to go ahead and plug these things in. Notice that the -1/6, this is just a constant hanging around here. If I plug in, let's see, t, this would be t to the -6th. And then I'm going to plug in 2 to the -6th. When I'm doing calculus, when I'm taking derivatives or integrals or things like this, I really prefer having negative exponents personally, right? Because then we can use the power rule and things kind of just flow a lot more naturally here. On the other hand, when I'm evaluating out functions and doing limits and things like this, I prefer not to have negative exponents. So quite often I will take a line to rewrite this here. Instead of t to the -6, this is 1 over t to the 6th power, right? So I'm using that negative in order to, apply the reciprocal here. So this becomes 1 over t to the 6th power. Again, some property of exponents here. And then this likewise will be 1 over 2 to the 6th power. Now we can see as t becomes very, very large, notice that it's very clear that it's in the denominator now. So as t becomes very large, right, we get 1 divided by a very, very large number raised to the 6th power, right? So it's multiplying by itself many times, right? So 1 divided by an extremely large number, well, this is going to be going towards 0. And we're just going to be careful with all this. And let's see, we have 2 negatives being multiplied together. So that's going to be a positive 1/6 times 1 over 2 to the 6th. And if you'd like to, you can plug this into your calculator or write at least this 2 to the 6th. You could throw in there what that's 64 times 6, right? You could get an exact fraction here, but this is someone in chat says that this is 1 divided by 384. Thank you very much, Burke. So yeah, you could enter, these things into WebWork if you'd like, or plug it into your calculator and get some decimal answer if you need to plug that into D2L. So what we're saying here, right, if you were to look at this, 1 divided by x to the 7th, it's kind of like 1 divided by x, where it's one of these almost hyperbola sort of deals. We're starting off at 2 and going off to infinity. And remember, whenever you do the antiderivative like this, some definite integral, you're doing the area under this curve. And so this is saying if you were to add up all the area from 2 and forevermore off to infinity, right, that this gets closer and closer and closer, it converges to 1 over 384th. So this, again, it goes to some nice finite number here. We would say that it converges, and better yet, we know what it converges to. It converges to this thing right here, 1 divided by 384. So that's why we say that it converges. Again, if it doesn't converge, then we say that it diverges. All right, so that's the first example here. I see a bit going on in chat. What do we have going on in the Q&A, Yuan? What kind of questions should we ask?
Someone is asking, can we just use the theorem that states 1 over x to the power b to say whether it's divergent?
Yeah, so that will tell you if it converges or diverges, right? So we got this nice theorem at the end of 7.8 that tells you exactly when. It's kind of like the P series sort of deal. It tells you exactly when this will converge or diverge. However, you'll find in many WebWork problems and also in D2L, possibly for quizzes and exams and whatnot, it'll say if it converges, state what it converges to, right? So the question isn't just does it converge or diverge, but actually if it converges, what does it converge to? And so with that theorem, you don't get what it converges to. And so yes, you can use it. However, if it asks what does it converge to, you still need to do all this work. But it's good to have sometimes multiple avenues to kind of see that you're getting the correct answer, kind of as a quick check on yourself. So yeah, knowing that is very useful. Good. Any other questions?
There's one asking, these are only for non-continuous equations.
So that's kind of one of the inspirations for improper integrals is evaluating definite integrals over non-continuous intervals here, or intervals on which the function is non-continuous. However, you also have these infinity sort of situations. Notice that this is it's completely continuous on this interval. Of course, if we were to include 0, right, then we would have some issues here, right? It'd be non-continuous or discontinuous at 0. However, on the interval that we've chosen here, it is always continuous. It's just this one's an improper integral because it goes off to infinity. All right, let's take one raised hand here, and then we'll go on to the next problem. Ian, you got the floor.
Sorry, I forgot this maybe in the intro videos, but why do you sub out the infinity sign for a t in the problems?
So for these ones, if you are going fast, there are I don't know, less proper ways of doing these. So long as you create and maintain some rules for what it means to plug in infinity, rather than, like here, we don't actually plug in infinity into anything. You would have to create rules like, 1 divided by infinity equals 0 and stuff like this, which many mathematicians will kind of cringe at. So yes, it is possible to escape this limit stuff and stay consistent with yourself. Formally, there are some subtle issues with this, but yeah, I mean, you can work it out for again, maybe 90-95% of the problems, so long as you understand things like 1 divided by infinity equals 0 sort of deal.
Okay, thank you.
Yeah, no problem. Okay, why don't we go ahead and try the second problem here. Again, a pretty nice one, all things considered. Notice that this is an improper integral, and so you do have to be a bit careful, just because we're trying to evaluate at 0. And of course, if you were to just plug in 0 into this function here, right, you would get division by 0, and that would be, an issue. And yet, maybe there's a situation where we have this, function that's going from 0 to 8 here. And, maybe when you add up this area right here, maybe it is actually a finite area. Maybe it actually converges. Or maybe, because again, this area is going to go off infinitely this way. Maybe when you add up all that area, it goes to infinity, like maybe you would guess. And so that's, again, we're trying to determine, does it go to some finite number, in which case we say it converges, or does it go off to infinity, in which case we say it diverges. What does this area do? Well, just like last time, I'm going to go ahead and, again, be careful around 0 and everything. I'm going to introduce this new variable, t. And in this case, right at this discontinuity, t is approaching 0. And because our interval is from 0 to 8, notice it approaches 0 from the right. So the limit as t goes to 0 from the right, it never really approaches from the left because that's not a part of this interval here. Now we're going to be integrating from t until 8. And I'm going to go ahead and do a bit of a rewrite. I'm going to write this as 5 times x raised to the negative 1/3 power. So again, the cube root, that's why there's the 1/3. And because it was in the denominator, that's why the negative exponent. And we're integrating this with respect to x. So let's go ahead and evaluate out the integral here. Again, the 5's kind of along for the ride. And when we integrate this, we raise our power by 1. So from negative 1/3 to positive 2/3. And then we multiply by 3/2. I included the 5 twice. That's going to be an issue. There we go. And we need to evaluate this from t until 8. So let's maybe collect all of our constants here. This is going to be 15/2. And let's see, when I plug in 8, I would get 8 to the 2/3 minus, when I plug in t, I'm going to get t to the 2/3. Now we can see that there's no issue plugging in 0 everywhere we see a t. And because we have a nice positive exponent here, right, raised to the 2/3 power, we're not dividing by 0 or anything like that. So that's quite nice. And 8 to the 2/3. Well, I know 8 squared would be 64. And remember, raised to the 1/3, that's just the same thing as the cube root. So I need to know what is the cube root of 64, and that's going to be 4. It's a nice even cube root here. And so there's a little bit of canceling happens, and it turns out that this area right here ends up, right, if you were to add up all of that area from 0 until 8, the total amount of area there is 30 units squared. And so this would converge. And better yet, we know that it converges to the finite number 30. Let me just show you here. Ian had just brought up this stuff, without limits and whatnot. This is a simple enough one that I think it would work out all right. So if I was to just take the antiderivative of this, again, we get 5x, oops, I forgot my 3/2, x to the 2/3. And again, this is a simple enough one that I think will be fine. And we just go from 0 to 8. Then let's see what we have, the 15/2. And if you plug in 8, you get 8 to the 2/3. And if you plug in 0, you get 0 to the 2/3, right? And this gives you the exact same result. So again, this is a simple enough one that you don't get into trouble or anything like that. But as they get more complicated, it is a good idea, and especially for partial credit and whatnot, to really show that where the discontinuity is, that this is an improper integral, and that it needs to be treated carefully. So I've seen folks been marked down before, kind of as far as not getting as much partial credit, I suppose, for not showing, this work with the limit and that it's an improper integral and all this sort of stuff. So that's kind of the only concern, right? So if you're going to take this, skip, make sure that you're confident in it and that you get the right answer in D2L, because if it comes down to, partial credit, you may not get as much on this sort of work here than if you were to show the limit and all that. Let's go ahead and take a few questions. Jeff, you got the floor.
Thank you, Professor. I did this and I came out with the same answer, but I thought I was perhaps wrong because of the theorem. Is it the interval of the theorem? Does it have to be 1 to infinity for it to apply?
Are you talking about for this whole 1 over x to the p sort of deal?
To be convergent or divergent?
Yeah. Yeah, so this only applies here if you're going from 1 to infinity. Now, it is actually fine. You can replace this 1 with some stuff. You can replace it with 2 or 3 or 5. You wouldn't want to replace it with any negatives, because then you're going to be encountering the discontinuity at 0.
Right.
But any positives, this will be true. So this is a question about going off to infinity.
Okay.
Right? However, our question was slightly different.
Right.
Our question wasn't about going off to infinity. Notice that infinity wasn't involved in either of our limits. It was just from 0 to 8. And then you have to, you can make up a new theorem for that. So,
Okay, thank you.
yeah, of course, no problem. Matthew, you got the next question.
Hi, yeah, I was just wondering how you know if it's going to be an improper integral. I know in this one, it's because you divide it by 0, right?
Yes. So there are 2 main things to look out for. One is if you have infinity or negative infinity, or both, in your bounds, right? So in this case, we had just 0 to 8, so it's a little bit hidden from us. But however, like in this one here, we know that it's an improper integral just because we see an infinity in the bounds. The other thing that you have to look out for is discontinuities. So exactly like you said, we have a discontinuity. If we just look at our function right here, if you were to try to plug in 0 for this, right, you'd be dividing by 0, and that's going to cause a discontinuity, right? 0 is not in the domain for this function. And so those are the 2 things to look out for, right? Discontinuities, integrating over a discontinuity, and integrating towards infinity or negative infinity.
Okay, all right, thank you.
Yeah, of course. One more here. Josh, you got the floor.
Hi, yeah, I was just kind of wondering, in general for the quizzes and exams, this example we're looking at here, number 2,
Yeah.
is this probably something we're going to see in terms of the difficulty level? Because I feel like one or two of the problems in the pre-class video kind of seem to have like a lot of steps and stuff. So is it something like this that we might see, or are they gonna get more complicated?
They get more complicated. Yeah,
Oh,
this is
okay.
still the warm-up page right here.
Oh, boy.
Page 1. We get we get what, like 1.5 days to cover this, and actually you'll see even on this one right here, we're going to be pumping up the difficulty level.
Okay. Thanks.
Yeah, yeah. Before we do this problem, Yuan, are there any questions in the Q&A that we should give some airtime to?
One is asking, how can you tell by looking at the function if it converges or diverges?
You can't always do it. I mean, if they're relatively simple things, you heard that some students alluding to this 1 over x to the p sort of deal. If you're integrating from like 1 to infinity or 2 to infinity, then you can tell. But in general, not so much. You can't really necessarily tell just by looking at it. You actually have to, put in some work, and then at the end you'll be able to say, right, that's the conclusion for these problems, is does it converge or diverge?
Another thing about the final grade, I'm not sure. Does the final calculated grade include weightings? Like, is it an accurate representation of our current overall mark?
Yeah, so the D12 gradebook does have all the weightings already programmed in. Yes. All right, why don't we go ahead and do this one here. Here again, we see that it is an improper integral because it has this negative infinity for sure. And so the question is, does this converge? If it converges, what does it converge to, right? It just says evaluate, or maybe it goes to infinity, in which case, right, we're going to have that it diverges. Now, if we were to go ahead and do the setup portion of this, right, we're going to have the integral from t to 0, and our limit of t is going to approach negative infinity. That's the issue here with this. And we're going to be evaluating out this integral x e to the 5x dx. So still, we need to find the antiderivative and everything of this. This should look pretty familiar for a problem that you may have seen in a previous section here in chapter 7. What is the technique in order to evaluate out this antiderivative here? Yeah, a lot of people are typing it in. Great job. Yeah, so this is a classic integration by parts style problem, right? We have a power of x times an exponential. So you can see how these things in chapter, in 7.8 can be comboed with really any of our previous sections from chapter 7. Or of course, you could get some u substitution or some nice ones where you just have to use like the power rule or whatnot. But this is an excellent opportunity to kind of test for two things just within, one problem here. And so, okay, in order to actually evaluate this out, let's maybe pull off to the side here for a second and just find the integral of x e to the 5x. And then we're going to, of course, plug some stuff into it. So in order to do this, we're going to let u be equal to x and dv be equal to e to the 5x dx. Again, pulling from all of our 7.1 knowledge, right, in order to choose these things. du is going to be 1 dx, and v is going to be 1/5 e to the 5x. So again, we take the derivative of u to get to du, and we integrate dv in order to get to v. Of course, we can double check if you take the derivative of this, you do indeed get back to where you started. All right, so according to integration by parts, this integral right here is going to be equal to uv. So I'm going to go ahead and write 1/5 x e to the 5x. So you see my u and my v, minus the integral of v du. V and du is the same as dx. So looking at this, yes, we can see that it is indeed easier to integrate that. And so we are going to be able to make some great progress with this. And so let's go ahead and do that. We have 1/5 x e to the 5x. And then when we integrate this, well, let's see, the 1/5 is along for the ride. And when you integrate e to the 5x, well, notice we already did that up here. You again get a 1/5 e to the 5x plus some constant of integration. But remember, we're about to be plugging some stuff into this. So maybe we aren't so concerned with that yet here. Okay, so let's go ahead and plug this in here. Now that we know what the antiderivative of this is. I'm going to need probably a little bit more room, so I'm going to move this off to the side a bit. We're evaluating again as t goes off to negative infinity. We just did the integral, so we know what the antiderivative of this is. It's 1/5 x e to the 5x. And then we have minus 1/25 e to the 5x. And again, we're evaluating this from t up until 0. All right, let's go ahead and plug some stuff in here. In particular, when I plug in 0, let's see, this is going to become 0. And let's see, e to the 0 is 1. So minus 1/25 times 1. And then we're going to go ahead and subtract away when we plug in t. So I'm going to have 1/5 t e to the 5t minus 1/25 e to the 5t. And again, we need to let t go off to negative infinity here. I think this one right here is fairly straightforward. Remember what e to the 5t looks like. I'm going to draw a small picture of it. Right? It just kind of looks like this standard e function, but it's been stretched a little bit by a factor of 5. But as you go off towards negative infinity, remember t is going off towards negative infinity here, right? This is going to get closer and closer and closer to its horizontal asymptote, which is at 0. So this bit right here is going to be going towards 0. Of course, this right is all constant and everything. So the only question is maybe about this one right here. Again, we just talked about how this piece right here, the e to the 5t, well, we just evaluated this, right? That's going to be going off towards 0. And we have this extra bit, this t, which again, t is supposed to be going off towards negative infinity. So this is negative infinity times 0. What is negative infinity times 0 again? I forget. Yeah, indeterminate. So yes, anytime that you have infinity times 0, this is one of the indeterminate forms, right? And so we need to spend a little bit of time trying to figure out how do I evaluate this? And you can see now that quite often these things segue into a L'Hopital's rule style question. So let's go ahead and write down what we have so far. We know that we have a negative 1/25. We know that we have minus 1/5. And again, we're trying to take the limit as t goes to negative infinity of t times e to the 5t. And then we have minus 1/25 times 0. That was our final bit. And so now the question is, how do we evaluate out this limit right here? And this is where you sometimes get into trouble, right? If you weren't doing this whole limit thing, right? And you were just doing, you know, the shorthand and plugging in infinity and plugging in stuff like that, that you don't see that really this is a L'Hopital's rule sort of situation. So, okay, we need to figure out how to evaluate this. Well, I'm going to go ahead and again, kind of pull off to the side here really quick for a quick side problem. The limit as t goes to negative infinity, and I'm going to rewrite this in a fraction form. Remember, we got lots of practice in 6.8 about L'Hopital's rule, writing stuff in fraction forms. So I'm going to go ahead and turn one of our exponents negative, in this case, the e to the 5t. I'm going to put that down in the denominator here. And now you can check that this is an infinity over infinity sort of situation. So this lines up perfectly for L'Hopital's rule. And L'Hopital's rule says we're allowed to take the derivative on the top and on the bottom. Oops, I forgot my negative sign here. And so when we take the derivative in the top and the bottom, we get 1 divided by, and this is negative 5e to the negative 5th t. And again, t is going off towards negative infinity, right? So, okay, there's a couple of things going on here. Maybe I'll just quickly look at this bit right here, e to the negative 5t. So if I was to draw a picture, we already drew a picture for e to the 5t. E to the negative 5t is very similar, but it's swapped around a little bit. It looks like this. So that is e to the negative 5t. So if I was to plug in a very, very negative number, you know, something like negative 1,000,000 or negative 1,000,000,000 or something like that, you can see that this is going to become astronomically large, very, very large here. And so we end up with something that's 1 divided by -5 times something that's very, very large, right? And in fact, very, very positive here. So again, thinking about, you know, like a billion or a trillion or something like this. And so if you take 1 and you divide it by something very, very large, whether that's positive or negative, overall, this is going to be going towards 0. And so all of that work there to say that this bit right here is indeed going to 0. And so our final result is -1/25 minus 0 minus 0. So that's a final answer of -1/25. And so at this point, right, someone had asked, how do you tell early on whether it converges or diverges? I didn't know for this one, right? It wasn't here until the very end that I can now confidently say that it converges. And better yet, I can say what it converges to. It converges to -1/25. But this is not something that we can necessarily see at the beginning of all this. Okay, I'm sure there are questions. This is maybe the first, like, you know, fairly difficult one that we've seen in the class notes. So let's go ahead and call on a few people here, see what's going on in the Q&A, and then we have maybe another problem that we can get to, at least started today. Aditya, you got the floor.
Hi, can you hear me?
Yeah, sure can.
All right. So can you like real explain like from how you transfer from the the graph you drew right on there, like where the e to the power of 5t, where you like highlighted those 2 portions? Yeah. Can you explain that part real quick again?
Yeah. So this is just knowing kind of what some basic graphs look like. So I know that e to the t looks like this, right? It's kind of one of these classic exponentials. It has a horizontal asymptote as you go off to the left towards -infinity. And it goes, you know, gets very, very large as you go to the right towards x equals infinity or so. And then that 5 doesn't really change a whole lot. It's kind of just stretching this out a bit. But still kind of as you plug in very, very large numbers, maybe they get very, very large a little bit faster by a factor of 5 faster. And as you plug in very, very small numbers towards -infinity, again, they get closer to -infinity faster by a factor of 5. And so it just kind of, it stretches a little bit. But again, the overall shape doesn't change.
Okay, I think I got it. Thank you.
Yeah, no problem. Let's do one more raised hand here and then see what's going on in the Q&A. Alex, you're up.
Hi, so I actually have a question about notation. Once you begin to integrate, is it standard to throw it in brackets and then put the, like, for example, the t to 0 like on the other side of what you're integrating?
I'm not sure if standard's the right word. I don't think it's not unstandard. I would say that the classic representation that I've seen for this is kind of with this large evaluation bar. Mm-hmm. But we need to be clear that you're evaluating out both of these things with these limits. And so I think maybe more standard notation or more correct notation possibly would be like if you bracketed this and then put the evaluation bar. Okay. But quite often I just shorthand that as, you know, just the brackets. But I mean, you could use parentheses too. Nothing's really fancy about brackets except they're a little bit closer to that straight evaluation line. Right. But I mean, you could use parentheses or whatever you'd like, and then just somehow denote that you need to plug in these things and subtract like you do for the fundamental theorem of calculus.
Thank you. I just like to make sure I know what I'm looking at exactly.
Yeah, of course. Always good to know that. Good. What's going on in the Q&A, Yuan?
One thing is asking, is it okay that the area under the curve was negative in this example?
Yeah, and in fact, right, if we were to just at least take some sampling points, remember that this starts off at 0, and right, the interval is all over here, right? -infinity all the way up to 0. So if you were to just plug in maybe some sample points for this, right? Well, if you plug in 0 into this function itself, right, you get 0. If you plug in like -1, you know, something that's in this interval here, Well, this x bit right here is going to be -1. And then e to the -5, this is something that's positive, but pretty darn close to 0. So you get -1 times something that's positive. So negative times a positive is going to be negative. And likewise, if you plug in -2, you get negative. And if you plug in -3, right, all of these values end up giving you negative. In fact, if you go to Desmos or your favorite graphing calculator or something like this, and you graph this thing, I think you get something that looks just like this. And so if you were to add up all of this area, remember, because it's below the x-axis here, all of this area gets counted negatively. And so maybe it isn't all that surprising, actually, given this picture, that you would get a negative result. But yeah, great question. Sometimes when you get a negative, that's a sign that maybe you did something wrong or you need to be a little bit careful here. But in this case, I'm actually happy that our answer was negative. Any other questions that we should talk about before we think about the next problem?
There's one asking, what if the bound was positive infinity?
If the bound was positive infinity, this would end up diverging. And I'll leave that as an exercise for you guys at home. So if you were, and you can do this, you know, from like 1 to infinity, or if you'd like a bigger challenge, you could do the -infinity to infinity. But these will end up diverging in these cases. All right, well, with that, let's go ahead and at least look at the next problem. This is, again, kind of another longer one. I don't think we're going to be able to make it all the way through this, but we should at least talk about some key ideas for this one. Again, kind of, we can see that this is an improper integral. And one place that you can see this is, of course, because of the bounds, right? We see this bound that it's going off to infinity. However, this thing has a fairly complicated denominator, and we should double check that we don't have any other discontinuities that we have to consider in our interval from 0 to infinity. And so one way that you could be dividing by 0 is if x was equal to -4. So luckily this isn't in our interval, and so we don't have to worry about that. Another way that we could be dividing by 0 is if x squared plus 1 was equal to 0. And if you rearrange this a little bit, you get x squared is equal to -1. And if you take the square root, you get plus or minus the square root of a negative. And this turns out to be a complex answer, right? And so luckily there's no other real place, in particular on the real line from 0 to infinity, that we would end up being dividing by 0. And of course, you could also have just looked at this and say, well, you have something squared, and then you're adding 1 to it, right? The smallest that can ever be is 1. There's no way you're going to be dividing by 0 with that thing. And so, okay, we don't have any other discontinuities that we need to be worried about. It's just really that infinity that makes this improper. And so the correct initial setup for this thing is going to be the integral from 0 to t. And again, we're going to take the limit as t goes off to infinity of, well, this integrand here, this 1 over x plus 4 times x squared plus 1 dx. And now we have to ask ourselves the same question that we did last time and that we do for all of these, right? How do you find the antiderivative of such a thing? And yeah, I've seen it alluded to a couple times here in chat as well, that yeah, this is a partial fractions style question, right? So we saw that we comboed in improper integrals with integration by parts, 7.1. And here we have a improper integral with partial fractions, 7.4. And so really you can kind of combo these with, you know, many sections here in chapter 7. And so just as before, we need to spend a little bit of time pulling off to the side and thinking about how do you find the antiderivative of 1 divided by x plus 4 times x squared plus 1 dx. And as you guys mentioned, this is going to be a partial fractions style question. So I'm going to go ahead and write this as the integral of, and the correct partial fractions decomposition is going to be a divided by x plus 4 plus bx plus c divided by x squared plus 1. So we have our two factors are x plus 4. That's just has a power of 1. So we only need this. And then we have the x squared plus 1. This is an irreducible quadratic. So remember, whenever you have this irreducible quadratic, you need the linear bit on top. So bx plus c rather than just a constant. All right. So, well, now we need to spend a little bit of time doing the partial fractions work. In the interest of time, I worked it out ahead of time, and I'll post the work for this. I need to write it out again and whatnot here. But why don't, for just us ending this class here, let's assume that I did things correctly, and we end up with a equals 1/17, b equals -1/17, and c equals 4/17. This would be maybe a good place for us to start our next class with, is maybe showcasing that we get these answers right here and where these come from, just to make sure, because again, kind of a lot of this week is review, right? And so it's a good idea to just, do this. So we're going to end up needing to integrate. Let's see, there's 17s all throughout this, or 1/17. So let's go ahead and take out the 1/17 from all of this. So this is going to become 1 over x plus 4 plus, and let's see, this b is -1/17. I already took out the 1/17, so, but still we need the negative. So negative x plus, and c was 4/17. And again, I already took out the 17ths over x squared plus 1 dx. So now we need to know how to evaluate this. We did this a couple times in 7.4, where kind of this one we can do quite quickly. This is just going to be one of these natural log sort of deals. So we're going to have 1/17 times the natural log of the absolute value of x plus 4. And of course, you can double check. If you were to take the derivative of this, you would get back to where you started. However, when you go to evaluate out this, right, this is quite complicated as it stands. And so we do actually need to kind of break this up. And this will help us integrate this. So I'm going to break this up, just across the numerator here. Negative x divided by x squared plus 1 plus 4 divided by x squared plus 1. And so maybe the last thing, since we only have, well, no time left, I suppose, in order to evaluate this out, we will need a u sub for this. So where u is equal to just the denominator here. And then this bit right here is going to be an arctangent. And actually, it's the nice one because it's just, x squared plus 1. And so it's pretty much just going to be exactly arctangent of x. There's going to be a 4 hanging around there. But this is how we're going to do those two integrals there. Then we'll have our antiderivative all figured out, and we'll be able to plug it back in. And then we'll be able to proceed with the improper integral portion of this. All right, but it is 2:40. That's a good place to end. Again, we get a couple days for these, for our sections here. And 7.5 is just called Strategies of Integration. And so we'll have, kind of a good sampler's platter, but we'll have kind of all of the techniques that we need. And then it's just a matter about staring at the main question of when do you know how to, which technique to apply? How do you know when you should be using integration by parts versus when you should be using trigonometric substitution? How do you know when you need to be using partial fractions, right? So we need to think about those sorts of questions because it's very possible that you'll just get a question on the exam that says evaluate, right? And it doesn't say what method to use or anything like this. It just says evaluate, kind of like this one here. And we had to decide that partial fractions was the right thing to do. And so that's what 7.5 is going to be all about. All right. Well, again, that's where we're going to end for today. We'll take a few questions here. And thanks for joining us, guys. See you on Wednesday, or if you come to office hours, Tuesday.